meeting is being publicly streamed.
Okay. Hello, everyone. Welcome to this live session. So today's topic of discussion is last time we discussed exam. Last time we discussed kernel range of a linear transform, and we also associated a matrix to a given linear transform. So today we will try to discuss. We will discuss more examples of it, and if you have any question from last week, you can also ask. So before we start, let me ask you uh, about the quiz. So let me take some feedback on the quiz. So how was the quiz? Uh, the difficulty level. How difficult was it, or how do you find the quiz? Or and what about the length of the quiz? Was it lengthy? Okay, you guys can unmute yourself and ask answer to me. Any opinion?
It wasn't that lengthy, but a few questions were a little tricky.
Okay, few questions for tricky. Can you uh, tell me in numbers, like one, two, of four question out of uh,
Four questions I couldn't answer.
four question you couldn't answer out of 10? Okay,
Yeah, out of 10. The rest, I think I've got them right. But yeah, sure. The four questions were a little hard. Yeah.
four questions. Okay, were they part of the MCQs or comprehensions or MSQs? Uh, what kind of questions were
One of them
they?
was an MCQ, and
MCQs.
one of them was comprehension. One or
Okay,
two
We
of
can
them.
better discuss this once we have the answer key because taking two, three subjects, we really don't remember properly each one of the questions, right? I mean, we just have an overview as of now.
yeah. So, what's your overview? What's your opinion on the word? I just want to ask
For me,
that.
it was very difficult. Maybe
Okay,
my
for you it was
preparation is
difficult.
not there. Yeah.
I just want to know the general opinion of people so that I have something to report to. Okay, so two people find it. One person find it difficult. Another it was moderate. Four question were difficult out of 10. What about others' opinion? Do you have any opinion on the exam? Was it fine?
I will say that probably I think it was doable. I cannot comment much because I was not regular in the classes.
Okay.
But then, particularly one question where I thought where vectors span was there were 4 5 options given. I was
Hmm.
not very clear on that, and it reflects back on me as well that probably I was not attending the classes previously. Yeah, but overall, I
Okay.
find paper was doable. I didn't find that hard that it shouldn't be done.
Okay. 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 Thanks. Uh, any other opinion? Uh,
Sir, actually, it was a combination of both difficult as well as easy questions, sir. And
yeah, that is supposed to be. That is it's supposed to be.
yes, sir.
Yeah.
Uh,
Uh,
one question
but
was
the
difficult.
difficult part was the point is like was difficult part was very difficult for you, or was it
Like
fine? Like it's
additive
if
identity.
you
There was a question on additive identity. We haven't solved such questions earlier. So, but it was
Hmm.
a little bit of thinking was required
Yeah.
and time also. So, not sure
Okay.
really, like everything will be right or not, but we have to discuss that later. So.
Sure.
But it was very interesting. So, paper was very interesting.
I
Okay.
agree with her. So
Good.
the identity, that thing, yeah, I agree with her.
Okay. Okay. So I would say it's paper was difficult for some and it was moderate for others. Um, okay.
It was the way we can expect from IITM, like we should have that concept clarity, and then we can
Hmm.
approach that.
Okay. Thanks everyone for the feedback. Um,
So we have a Python session as well now, and we have our programming exam coming up. So there's a clash between math and Python. So what do we do?
when is your class? Like, I think this is the live session for this course, right?
Yeah, same thing. For math and Python, it's 10 to 8 to 10.
Both on the same day.
Yeah, same day, same time as well.
Okay, I don't know what to, but I will try to forward your request. So what? So you want to attend both of the sessions, but you are not able to because both are on the same time,
Yeah,
right?
both.
That's what you
Yeah,
are.
yeah. And we have a
Okay.
programming exam as well. So
Okay. Programming exam right now, or
no,
it's
no, not
coming next week
now.
or something? Okay.
Yeah, next week in like 5 days.
Okay. All right. Um. Yeah. Um. All right. Okay. So let me start with revising. Yes, Karthik.
Sir, I attended the Max 2 session yesterday, and I had about 16 questions in total, but you said
Okay.
only 10.
No, no, I like the 10 questions were there, but there were parts also. So maybe you are counting the parts, sub parts as well.
Oh, yeah, yeah, yeah. Like there is a question around like pen pencil purchase with Shakti as an example,
In
and that
that,
have like
in
three
that,
questions.
that is the 10th question, and in that it has three parts. So, right. So if you are counting the parts also, then it will add up to 16. I don't know. I'm just looking at, uh, yeah, the outside number.
For
I'm not
me,
counting the
the
parts.
paper, I didn't, I didn't conceptually attend the linear transformation, which was the first question is around. So except that, rest all seems to be okay.
Okay, good.
Which
Sir,
week we are starting today, or is
sir,
it?
better will be you show the paper and we can discuss the paper because right now we don't remember all the questions also.
Okay. Uh,
If you have
I think
paper,
this,
because
yeah,
we
I
don't
do have.
have paper right now.
Okay. Westrilo. I don't know if you have raised your hand. Do you have
Morning.
something
Yeah,
to say?
yeah. So I too took the exam.
Yeah.
I think the general feedback I also agree. But when we start preparing and attending the sessions and all I think most of us, many of us are 100% of the people will start preparing to get 100 out of 100. That's the general understanding. Where everyone put effort to get 100, but finally very few will get the top, and only the people will fall 50%, maybe some less than 50%, somewhere above 50%. That's the general. But I think what the challenge, what I'm seeing is, by the time we are try to understand the weekly sessions, attend and try to digest, and then try to solve some problems. I know loads of information, loads of question banks are there. It's only a matter of time you sit and start working through each and everything to get that confidence. But by the time you achieve that confidence level to hit that 100% mark, I know it's not practical for everyone, but even if you try to attempt to get 100% prepare against that, you don't have time to really master it, to really
Mm.
address all the questions in the exam. It's not a matter of time. It's a matter of how confident are you in terms of solving those problems. Do you have enough time? So what's important for me to ask is, if someone in this group are able to achieve that above 80 or something, what is the methodology they are using in preparing? Are they really conversant with this type of subject earlier, and that's why they're able to address it quickly? Or is it that they have a different way of preparing for the exam? Maybe you can help us, or maybe students who are already done this and able to achieve, what is the technique? Because what I understand, where I try to struggle is, I'm able to understand the concept. By the time we start working through the problems and try to get some confidence, the exam is in front of me, and I need to go and attend the exam, and then we know what is the outcome of that. It's not. I'm not saying I'd done pretty bad. It's okay, but I was aspiring for better than that. But I couldn't. No, I know I couldn't go there. So most interesting thing is, rather than asking how did you do, I think we should understand how other who are able to achieve that higher score are able to achieve that in a shortest point of time. That's, sorry, a lengthy discussion, but that's what I just try to. I don't know how many are concurring with this feedback, because most of you are much younger than me. Okay.
That thanks for your opinion. What I feel is, if you like, if you attend the TA sessions, because in TA session they discuss problems, and in the live sessions as well. Uh, in the live session, you kind of revise whatever the material of the material of the week, and then in the TA sessions they discuss the problems, activity problems, and then there are all list of that. So I find the question bank is pretty good. If you try to solve those question bank itself, you try to understand like how many different type of problems can be there, right? And in mathematics, there is no one type of question. I, uh, there are like infinitely many possibilities of question that you can make. Okay.
Sorry, which question bank did you mention? Is it something that
No, question bank. I meant you find it on the course page. Okay, there are activity problems. Then there is assignment that need not to be submitted. So if you do those things after just looking at the lecture, you do the activity problems, and then you try to find complete solutions and all. Then it will enhance the understanding. Okay. Right now, I don't know what's the syllabus of quiz two. I will let you know once I have that information. So I think then it will be easier for you to understand each concept. So just break week-wise topic into uh, yeah into smaller subtopics. For example, linear transformation, and then kernel, and then uh, range of the linear transform, and then try to solve problem for each of that subtopic. And once you do that, you will have the understanding of each subtopic. That's what I used to do when I used to take these courses. And you are completely right in saying that it is very difficult to master these concepts in just one go. By just weeks understanding, you cannot master a topic like linear transform or vector spaces or basis or spanning set, because there can be different type of question, there can be different type of setup, there can be different type of examples that might be struggling to solve it. But uh, but yeah, as time passes, as you do more and more practice, your understanding of the concept becomes stronger and stronger. So it's completely on that. So
Yeah, I understand.
Yeah.
One other interesting thing I observed is, while doing maths 2, the concepts
Right.
of maths 1 is, I'm able to understand the maths paper concepts much better in maths 2. So that means it's a matter of time. So as you keep going to the next level,
Yes.
the earlier levels
Right.
are looks to be very, but when we are doing a maths 1, giving a maths 1 paper, the confidence was not much. But whereas when we're doing
Right.
maths 2 and reflect back on maths 1, probably because of the
Right.
time or the repetition, the
Hmm.
ability to understand or ability to appreciate and do the problems are fast. I think that's one another observation. I know this is nothing to do with examination, but it more of a learning experience. Sorry, maybe it's not a right
That
forum
is
to
good.
express.
That is true. Mathematics subject is of that nature. So more practice means more uh, like understanding of the topic. So that's how. Okay. So let's come back to today's live session. I think we have enough discussion about quiz two. Um, so let me. So this is the week 6 of second session of week 6. In case you are wondering.
So
Okay.
would there be a recording for last session somewhere? Because I missed that one.
It's on the YouTube channel. You can always go back and look at it.
I mean, sir, would it be okay for you to just share the link? Because in YouTube, how do I search for it? I'm so sorry if I'm just.
So when you go into your calendar, when you are joining take the link to join from the calendar, there is one link, an Excel sheet link just below that. So you click on that, it will open an Excel sheet. In that, all the links are there. It's very easy.
Oh, okay, sure. Thank you.
Is it clear? Should I share the link as well?
Okay, let me just check when I'm going from calendar. But anyway, sir, let us continue. I mean, I'll do it sideways and I'll try to put it on the chat.
Someone shared, I guess.
Yeah, Jitendra Sachdeva. Thanks, Jitendra. Okay, good. Yes.
Okay, great.
So last time we have discussed. So we have already discussed linear transformation in week 5. Linear transformation or linear maps in week 5. And then last session we discussed how to associate a matrix to a linear transform. All right. And then we also discussed the kernel of a linear transform and the image or range of a linear transform, as well as we also proved the Rank-nullity theorem. Not we saw the statement of Rank-nullity theorem of a linear transform for a linear transform. Okay, so let me quickly recall this one by one. So linear transform map T from V to W is said to be a linear transformation or a linear map. It satisfies the linearity property. First property is that TV1 plus TV2 is equal to TV1 plus TV2 for V1, V2 in V, and T alpha V is equal to alpha times TV for alpha in R and V in V. Some examples of the linear transformations are T from R2 to R2 defined to be Txy equal to x plus y 2x. Okay. So it is a linear transformation. Now look at this another example.
Sir,
Yeah. Yeah.
sir, is this session will be recorded?
Yes, this is recording. There is a recording going on. Now, is this map Txy equal to xy times xy comma y? Is it a linear map?
No, sir.
It's not.
No, it is not a linear map, right? So now you know what is a linear map, what is not a linear map. So it is a linear map. So top one is a linear map, bottom one is not a linear map because it won't satisfy the property x, the linearity property. You can check that. All right. Now we also saw that T being a linear is a linear map or linear transformation is equivalent to proving that just one condition, which is TV1 plus alpha V2 is equal to TV1 plus alpha TV2 for V1 for V1 V2 in V and alpha in R. So you don't need to prove both of the conditions separately. You can just prove this single condition and then it is okay. All right. Now, then we saw how to associate a matrix to a linear transformation. We saw so for that we need to start with an ordered pair, ordered basis. So ordered basis of domain and codomain. So we want to associate a matrix to a linear transform. Suppose you have a linear transform map from V to W, okay, and let beta be the set of vectors V1 to Vn, and B basis be an ordered. Why ordered? Because they are written in an order, okay, V1 up to Vn. So if I change the indexing among them, then I will have another uh, ordered basis. Okay, so that's why the numbering or the ordering is important. That's why I'm writing ordered basis, not just any basis. Ordered basis of V and gamma, which is gives us a set of B an ordered basis of W. All right. So now, with respect to the ordered basis of B and ordered basis of W, I want to express my uh, given linear transformation in terms of a matrix. Okay, and how do we do that? So first step is to have have a clarity of basis of domain and codomain. So if you want to recall, this is V vector space V, which is on the left hand side, is called the domain space or domain set, and on the right hand side, it's called the codomain. Okay, so beta is a basis. So beta is a basis of domain, and gamma is a basis of codomain. Okay, now in order to express the matrix, I need to write down the basis of domain in terms of basis of codomain. Okay, now what does it mean? So I will write down V1 in terms of WIs. Okay, so all right, and I will express each of that with respect to the basis of WIs. All right, and now third step is to write down the matrix. So how to write down the matrix? So matrix, associated matrix A with corresponding to T is nothing but writing each of the. So from here you get a column. Okay, what is that column? The columns are nothing but the coefficients, which is A11 up to AN1. All right. Here also you will get a column for each TVI. You get a column which is formed by the coefficients of the vectors. So A1N up to AMN. Sorry, M1. All right. And now you place these columns to form this matrix. Okay. So in other words, you get A11 to M1 and A1N up to MN. All right. Now so this looks abstract. So now let us look at an example to make things simpler for you to understand. So let me take the same example that I gave earlier. So let me take this and place it here. Now let's see this example, how to write down this. Okay. So first step is to have a ordered basis for domain and codomain. So in our case, so let me start with beta, the standard basis. Let me take both of them. Let beta and gamma be standard basis of R2. Now, what are the standard basis of R2? Can anyone tell me?
1 0
0 1 and 1 0. 1 0 and 0.
So I'm
0 1.
taking this order. Yeah, I'm taking this order 1 0 and 0. Okay, so gamma and beta both looks like this. Now I want to express this linear transform in terms of the standard basis. That's a step 2. Now step 2 is writing basis of domain in terms of codomain, in terms of basis of codomain. All right. So now what is the basis of domain? So let me start with first vector, T of 1 0. Now what is T of 1 0? What is T of 1 0 if I place?
It's 1 2.
1 2.
It's 1 2. Right. Now what about T of 1 0 0 1?
1
1
Right?
1
1 0.
0.
No, it's 1 0. Right.
Yes, it's 1 0.
Now what are the yeah. Now I want to express 1 comma 2 vector with respect to the basis of codomain. Now what are the basis of codomain? Basis of codomain is again standard basis. So now how do I express 1 comma 2 vector in terms of that? 1 times 1 comma 0 plus 2 times plus 2 times 0 comma 1, right? And what about this other vector 1 comma 0? It is 0 times 1 comma 0. Sorry, it is 1 times 1 comma 0 and 0 times 0 comma 1. Now what will be the matrix? Matrix is
1 2.
matrix is right 1 2 and 1 0. Right, the columns, it will become the column. The first entry is going to be the column. So let me write it. T10 will be the first column. T01 will be the second column. Now what is the first column? 1 2. Second column is 1 0. All right. So this is how to express it into this. Now let me work with the same linear transform, but change the basis.
Sorry,
Okay.
sorry. Can you please repeat that previous step, please? 10.
Yeah. So what was the
basis
last
I
step?
understood.
Yeah, the last step of this, we write the AT. The column of AT is nothing but the image of TV1. Okay. So the column of AT is nothing but the image of the first basis and then the image of the second basis. So what is the image of the first basis? First basis image is 1, 2. It gives you we just need to note down the coefficients. It is 1 and 2. So 1 is the 1, 2 is the column. For the second basis, it is 1, 0. 1, 0 is the column.
Yeah, by T10 given has given 1, 2, and T01 has given 1, 0. That step is clear.
Right.
So you have just taken
Right.
the 1, 2 and written in a black color. The top 1, 1, 0 you written in the black color. So my question is how from where did you get this? After the black numbers, the blue numbers, that is where I'm confused. The 1, 0, 0, 1, 1, 0, 0, 1.
Don't get confused with the colors. It is just you can just take. It is same. The color is not important in this case. I'm just expressing it in order to show that it is.
Oh, you're
distinct.
okay.
Yeah.
Okay.
Now it is fine. Is it look fine now?
Yeah. 1, 0, 0. Yeah, clear. That's why I was confused. Okay.
Yeah, the color has no importance.
Yeah, go ahead, please.
Yeah. So now let me change the basis. So instead of taking the standard basis on both ends, now let me take some different basis. Okay. So and work with the same example. So same T, but different basis. So let me take now in the first step the basis to be 1, 1 and 1 minus 1. Okay, let's see whether this works or not for this basis. Yeah. So let me take my gamma to be okay. So let me take beta to be the standard basis, and let me take my gamma to be this basis, which is 1, 1 and 1 minus 1. Now beta is the basis of domain and gamma is the basis of codomain. Okay. So now step 2 is, so what is the standard basis? Standard basis is again going to be 1, 0, 0, 1.
Sir, I have a quick question here. So when you say that you are trying to write the transformation matrix, so before the writing out the transformation matrix, when we say that when we're expressing the basis of domain in terms of the basis of codomain, so you take this, so this is the image, so this is, so when we say this, that we express when in terms of codomain, so this 1 and 2 that we, so 1 comma 2 that we get out of the transformation, so shouldn't we have written that we are expressing the codomain in terms of the domain, because 1, 0 and 0, 1 are the basis of the domain, right?
In this case, in the previous example, look at this. Beta and gamma both are standard basis. Okay, so both base in both of domain and codomain have the same basis, the standard basis. So
okay. And
but now,
so 1 comma, yeah, sure. So this 1 comma 2 and 1 comma 0 after the transformation has occurred, so this is the codomain, right?
1 comma 2, yeah, this is in codomain. This is what you're saying, right?
Yeah, right.
This is in codomain,
So,
right? This is in R2, right? Codomain.
Yeah, this is in W, and this 1 comma 0 is also in W. So now what we are doing, what we are trying to do is to express this codomain in terms of the basis, of the domain, right?
No. Now this is in codomain. Now I'm expressing 1 comma 2 in terms of the basis of codomain. Okay, now in this case, basis of codomain is one standard basis, so you get the same coefficient 1, 2. Okay, so now let me work out another example where I change the basis of codomain so that you will get different coefficients, not 1, 2. Okay, you are getting confused because this and this looks same, right? That's why you're getting confused, if I understood it correctly.
Yeah, so
Because
my point was that when we are trying to feed in the inputs like for x and
Hmm,
y, so those
hmm,
should be the basis for the domain, right? So after the transformation has occurred, it should give me an element in the codomain. So, but
that is
when we
true.
are writing, yeah, when we are writing down the transformation matrix, the elements of the transformation matrix are the elements of the domain, right?
No,
Written in
what do you mean
terms
by
of the domain.
element of matrix? So what is the element? Element is a real number. It is neither in domain nor in codomain.
So, but when we say it's this T10, this
Yeah,
T10 is the codomain, right? Is the element of the codomain.
right.
So technically,
Even
when we say,
codomain.
yeah, yeah, and this T01 is also the an element of the codomain, right?
Right,
So when we try to write the matrix, this transformation matrix should take the elements of the codomain.
right.
So this 1, 2, and 1, 0, these are the coefficient of those transformation matrix in the codomain, right?
Yes.
Yeah, so that's why I was thinking about why do we say that we are writing the basis of domain in terms of the basis of codomain and not saying that we are writing in terms of the basis of codomain in terms of the basis of domain.
No, we
Why
are
don't we
writing
say that?
basis of domain in terms of codomain. Uh, okay, so let me be more precise. Writing image of, uh, I think this is where you were getting the image of the
Ah,
basis.
yes, yes, yes. Now it's now it settles. Yes,
Oh, yeah,
yes,
yeah.
yeah.
I think yes, yeah. It is from my end. It is problematic. In particular, I'm writing the image of the basis of domain in terms of the basis of domain. Right.
Yeah, yeah, yeah.
So
That's fine. That's fine. Yeah, that's good. Thanks. Thanks.
now, image. Let me. Thank you for that class. Image of the basis. It might be confusing to others as well. Okay. Sorry for that confusion. I was writing the image of the basis of domain in terms of the basis of codomain. Okay. So now let me change the basis of codomain. Instead of taking the standard basis, let me take this new basis 1, 1, comma 1, 1, vector 1, 1, and 1 minus. Okay. And let's see what happens. So my function is same, which is x txy is equal to x plus y and 2x. Right. X plus y comma 2x. Right. So now, if you express 1 comma 0, so now again we need to write down the images of the basis of domain in terms of basis of codomain. Okay. So image of 1, 0, which is the basis of domain. If I write it down, I will get 1 comma 2. Right. Now I need to express it in terms of basis of codomain. So it is going to be something a times 1 comma 1 plus b times 1 minus 1. Now what are the values of a b? What is the solution of this system of linear equation? Can anyone tell me?
So a plus b equal to 1 and a minus b equal to 2. So we'll have two equations.
Yeah. So it is a plus b equal to 1 and a minus b equal to 2. Now what is the solution of this equation?
So a will be 3 by 2
Right.
and b will be minus 1 by 2.
Right. Right. So you get a and b to be this. In other words, uh, 3 by 2, 1 comma 1 plus minus 1 by 2, 1 comma minus 1 is the expression of t 1 comma 0. Right. Now similarly, we would like to express the image of 0 comma 1 on another basis. It is 0, comma 1, image of 0, comma 1 is 1, comma, right? Now again, a 1, comma 1 plus b 1, comma minus 1. Now it is going to be what is, now how do we express in terms of this? What are a, b?
So a plus b equal to 1 and a equal to b. So b equals to half and a equals to minus half.
So it is half 1, comma 1 and half this, right? And now what will be, how will my matrix will look? So you just need to write down these coefficients. So this will correspond to the matrix 3 by 2, 1 by 2, and this will correspond to the matrix half, half, right? Sorry, this will correspond to the column vector half, half. So I will get AT equal to 3 by 2 minus half, 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 right? Now, as you can clearly see that you obtain a different matrix corresponding to the same linear transformation. Okay. So the choice of bases become important. In this case, you had 1, 2, 1, 0 as columns, but in this case, you have 3 by 2, minus 1 by 2, and 1 by 2, 1 by 2 are the choices of the column. Okay. So now let me do one more thing.
I have another question. So when we are claiming that the image of my basis of the domain, and we write them in terms of the basis of the codomain, are we also like implicitly considering this transformation to be a surjective one?
No, it need not to be surjective. I will give you examples. For example, in case of there can be while writing, because these coefficients need not to be non-zero always, right? They can be zero also. So in that case, you won't get the surjectivity. For example, you can have, let's say, t x comma 0. Okay, your image of this xy. So in this case, again, you need to express 1 comma 0, t of 1 comma 0 in terms of the basis gamma. So you will still get some coefficient AB, but that map is not subjective. So you are not implying subjectivity anyhow. I'm just, in order to obtain this matrix AT, you need to have these things. For example, if you take this, and if you want to express t of 1 comma 0, which is going to be 1 comma 0, and now you want to express it in terms of gamma, so which is 1 comma 1 plus minus 1 comma 1, a times this, b times this. Now what will be the images? So it will again be half half in this case. And if you take t of 0 comma 1, so you will get 0 comma 0. Now what will be the a comma b? It will be 0 0 in this case. So the matrix will be half half 0 0. So but it is not a surjective clearly. So it is nowhere hinting that it is surjective. Yeah, you may think it might come to you because in these cases these are surjective map, these are nice map, these are in particular isomorphisms, but it not to be true in the general case. In generality, if I look at examples, this might not imply that. But what we are seeing is that the order of the basis is important. Okay, and if you change the basis, then the corresponding transformation, the matrix will also change. All right, so
So I have a
this is,
doubt.
yeah.
I understood all of the calculation parts, but how is the first example different from the second one? Like, why do we have to find A and B value in the second one, but why not in the first one?
Because in the first one, you can again do that, but it is clear, right? If you want to express 1 comma 2 in terms of the standard basis. So what are the coefficients? It is 1 and 2. That is,
Okay.
it is very clear from this thing. But it is not clear if you want to express 1 comma 2 vector in terms of this strange looking basis, which is 1 1 and 1 minus 1. So then you need to, because you want to express this, so in terms of the basis, in terms of these bases, That's why you are writing it you are using these variables a and then you are getting some system of equation and then solving that.
Okay, so if
It
it's a
will be
standard
obviously
basis, we don't have to do that, the calculation.
in terms of standard because you can do that computation, but it is not necessary. You can just if you write it like a is equal to 1 comma 0 plus b times 0 comma 1, you already know the answer. A is 1 and b is 2, right?
Okay,
You don't
okay,
need to
okay.
do that
Oh, okay,
as
okay, okay. Sorry. Yeah, that was
right.
nice. That was easy. Yeah.
Yeah. So in that case, it's trivial. That's why I'm not. That's why it is not preferred to do it. All right. So uh, let me discuss. Since we are discussing examples, let me discuss one more example to you because anyway, I was trying to discuss some examples only because we have already discussed the theory last time. So let me pose it as a question. A W is a uh, yeah W is a vector space is a subspace of R3 given by this. All right, and beta, which is 210 and 100 101, is a basis of W. Now define a map. Let T be a map from W to R2 given by T of 21201 equal to 1 comma 0 and T of 101 is equal to 0 1. Okay. Now question is, what is
Sir, it is
the
210, T of 210 or 201.
oh let me check. Yeah, should be 210.
So here
Yeah,
also we have to.
yeah, it's 210. Right. Now the question is to find out the matrix corresponding to this linear transformation. All right. So what will be the corresponding matrix? Can anyone tell me? First step is to know the basis. So for W, we have so first of all, this linear transformation from W to R2. So for W, we have beta, and for R2, we have the standard basis. All right. Now,
So it is a 2 cross 3 matrix.
it is 2 cross 3 matrix. Okay.
So,
But what are the entries? That's what I'm asking. So for that, first we need to write down the basis T of V1. Now, what is the basis 210? I need to express that in terms of the basis of
1 comma 0.
codomain, right? Yeah.
Yeah.
So it is, what is the image of this 210?
1001.
It is 10, right?
Yeah.
Now,
Yes.
what are the coefficients? I want to express this image in terms of the standard basis. Now, what will be the image? What are the coefficients of that? Of R2? It is 1 times this and 0 times this, right?
So the codomain, if the codomain base is not given, we should assume standard base. Is that an assumption? Right?
Yeah, you can assume that. But in this case, I have given you that R2 has a standard basis. I have written here that
Yeah,
R2 has a standard basis.
yeah, sure.
So now, what is the first column? First column is going to be What is the first column?
1 0. 1 0.
1 0. And now what about the second column?
0 1.
Again, yeah. Again, I need to express this with respect to the standard basis. And if you express that, you will get 0 1. So the corresponding matrix AT is 1 0 0 1. Right? So this is what it is. Now, let me change the basis of codomain. Let me take gamma, which I defined earlier as well. So let me just copy all this. I don't want to write it again. Copy. Paste it here. Now, instead of taking the standard basis, suppose R2 has basis given by gamma 1 1 and 1 minus 1. Then what is the corresponding matrix to this new basis? So again, the exercise is the same. We first need to express the basis, the images of the basis of domain in terms of the basis of codomain. All right. So what is 2 1 0? It is 1 0. Now I need to express 1 0 in terms of the basis of codomain. So that is A times 1 1 plus B times 1 minus 1. All right. Now what are the solutions of AB?
Half and half.
Correct. Half and half. Okay. Now what about 1 0 1, which is 0 comma 1? Now what I want to express 0 comma 1 in terms of again gamma. So how do I express that? It is
Minus half and half. Half and minus.
minus half, half and minus half. Right? Now what will be the matrix then?
Half, 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 minus half.
Half, 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 minus. Right. So this is the matrix. So this example is clear to everyone?
One question I have is
Yeah.
T210 translates to 1 comma 0. Can you explain how the transformation? You're substituting the values into x is equal to 2y plus z, or
No, this is the definition of this is already given to you.
oh, okay,
This
okay,
is the
okay.
definition.
Good. Fine.
Yeah. Right. Any other doubt?
Sir, actually, from R3 to R2, so it will be a 2 cross 3 matrix. But so how basis the change order basis you did, right? For a gamma basis you did it. So why not? Why it is like a 2 into 2 only? Like
Yeah, because if you were taking any vector in this in W, then you will be expressing with respect to these
yeah.
element, and then so for example, if you're taking any vector, let's say V in W, then the corresponding vector you will express with respect to this V1 and V2. Okay,
Yes.
let's say A times V1 and B times V2.
Yes.
All right, and then you will be multiplying this AB. to this matrix. So it will be 2 cross 2 because this is a two-dimensional subspace of R3, and you are mapping a dimension 2 vector space to a dimension 2 vector space. So the corresponding matrix will be of the form 2 cross 2. Is it clear now? So it's a
Yes.
two-dimensional vector space. So, and while multiplying any vector, you need to first express. You cannot just directly multiply x, y, z. You need to express x, y, z in terms of this vector, and then you will get two coefficients, which will be the let's say AB, and then you multiply that.
So what are the bases they are given? So that basis has to be a linear combination of these coefficients A and B.
Right.
To the
So
got the transformed vectors.
yes.
Yes.
For example, if you take another vector which satisfies this equation, then you need to, for example, one. Let's say this vector, 3, 1, 1. Okay. So this vector is in W. Okay. And if I express 3, 1, 1, it is precisely 1 times 2, 1, 0 and 1 times 1, 0. So I get 1, comma 1, this matrix, this vector corresponding to this
Okay.
this element.
Coefficients. Okay.
And I will be multiplying this while applying to this matrix. Okay.
Okay. Got it.
Yeah. Good. Thank that you pointed out. I missed that part. Thanks. Yeah. Now I have another question. Suppose you have a linear transformation from R2 to R2 given by T R2 to R2 and beta, and with respect to the standard basis of R2, V as domain and codomain, E has this expression A, B, C, D. All right. So for the corresponding matrix AT has this expression. Now, what will be the matrix? Okay, find out A corresponding to gamma basis of domain and beta basis of codomain. Okay. So yeah, is this question clear to you, everyone? So we have given a
Basically, you're asking, you're giving a transformed matrix and asking to reverse to the original A. Is it?
No. What I have given, so we have given a linear transformation T,
Right.
and corresponding to T, there is a matrix associated where I have taken the basis of domain and codomain to be the standard. Now, I am saying what will be the matrix A if I change the codomain, if I change the domain's basis to this gamma and keep the basis of codomain to be the standard ones. Now I need to find out the corresponding matrix A. Okay. Find out the matrix associated. Let me rephrase it in better way. The matrix associated to t with respect to the basis gamma of domain and beta of code. Now this question makes sense. Okay, now how do I change this? So in order to for shorthand notation, let me use this notation because basis of domain and codomain are beta and beta. So I will write I'm writing this matrix as T beta beta. Okay, where first beta is domain basis, second beta is codomain basis. All right. Now, what I want to find out, I want to find out T gamma beta. All right, because domain basis I want to be gamma and codomain basis is beta. Okay, so this is what I want to find. Okay, this new notation is fine to everyone. Now,
Yeah, makes sense.
right? So now let me explain how do we do that. So again, uh, so this matrix AT, so this T beta beta is given with respect to the standard basis. In other words, if I multiply x comma y, if I find out the value of x comma y of t, it is multiplication to this matrix. So it is going to be ax plus by cx plus dy. All right. Now this is the actual linear transformation. Okay, this is the expression of the linear transformation. Now I want to express the images of domain, basis of domain in terms of the basis of codomain. So what is the domain basis? It is 1, 1. So what is T11? T11 is, what is T11?
Is it ax plus by?
C a plus b plus and c plus d.
Yeah, it is not x and y. You are replacing x and y. So it cannot be in the expression, right? You are writing x equal to 1, y is equal to 1. So it cannot be in the expression. So it is a plus b.
Yeah.
And what about T1 minus 1? What about T1 minus 1?
A minus B, C minus D.
That is true. Now, I would like to express this vector in terms of the codomain basis. Now, what is codomain basis? It is beta. All right. So, codomain basis is beta, which is nothing but the standard one. So, what are the coefficients? It is going to be a plus b 1 0 plus c plus d 0 1. Right. And similarly, you can write down the coefficients of other vector as well. So what will be my T gamma beta? It will be a plus b, c plus d, a minus d, c minus d. All right. Is this clear to everyone?
Sir, like when we are taking from the matrix, don't we take like the columns like A, C, like AX plus CY?
No, no. If you multiply this, so how does this Txy define? Txy is defined as a multiplied with xy. Okay. So it is going to be ABCD multiplied with xy. So AB multiplied with xy. So it is going to be AX plus BY and
Okay,
CX
okay, sir.
plus BY. All right. Okay. Now if you are familiar with the notation of beta and gamma, beta and gamma, so let me find out another gamma gamma. Okay. Now, what will be gamma gamma? So, what is gamma gamma? It is domain basis is gamma and codomain basis also gamma. So, in this case, again, I need to express the image of the domain basis with respect to the basis of codomain. So, what is the basis of domain? It is gamma. So, in other words, T of 1 comma 1. T of 1 comma 1 we already know. It is A plus B, C plus D. All right. But now you need to express A plus B, C plus D in terms of the basis of gamma, the basis of codomain, which is gamma again. So it is 1 comma 1 plus T 1 minus 1. Right. Now it is solving this system of linear equation. Now, what are the solution of this system of linear equation? So first of all, what are the system of what are the linear equation that you obtain?
Yes. So you have a plus b equal to s plus t and c plus d equal to s minus t. So from here
Right.
you can get
S plus
s
T is
equal
equal to A plus T. S minus T is equal to C minus C plus T, right?
yeah. So you get s equal to a plus b plus c plus t by 2.
Similarly, T is going to be A plus B minus C plus T divided by 2, correct? Right. And now, what is T1 minus 1? T1 minus 1 is going to be, just replace here, T1 minus 1. Now, what we will get?
Minus b and c minus t.
Right. We will get A minus B, C minus. And what will be the S and T? It will be A plus C minus B plus T by 2, and T will be A minus B plus uh, A plus D minus B plus C by 2. All right, is it clear? How will I get this? Is it fine? And now I can write down the matrix, which is P gamma gamma. I can write down. So just fill in the blanks. A plus B plus C plus D by 2. A plus B C plus D by 2. A plus C minus B plus D by 2. A plus D minus B plus C. All right.
So again, the same doubt. We've taken S and T here, but there we haven't. The previous example.
Yeah, because in the previous, again, we had the standard basis on the right
Standard
hand on the
basis. Oh,
codomain.
yeah. Sorry.
Yeah, again, the same answer.
Sorry. That was
So,
common sense. Sorry.
no, it's fine. It is fine. It is fine. You can ask these questions. That's completely okay. Okay. So, I hope these things are more clear to you guys right now. Now, I also discussed kernel last time. So, let me quickly recall kernel. Kernel of a linear transformation T from V to W is shorthand notation is KER in brackets T. It is set of all vectors of V such that T of V is equal to 0. Clearly, it is a subspace of subspace of vector space V. All right, that's the definition. All right, yeah, and some examples that we saw was that kernel of
So does this
a zero map.
imply? So, sir, just a quick question. Like, does this imply injectivity in the first place? So this condition that TV equal to 0.
No. For injectivity, I will write down the equivalent condition when kernel in terms of kernel. The injectivity condition in terms of I will write down. So kernel of a zero map is what is the kernel of a zero map? Anyone?
It's
Is
zero
it
itself,
0?
right? It's zero, right?
No, kernel of a zero map is not zero. It is the whole space V because every element is in kernel, right? Now, what about kernel of the identity map from, let's say, so kernel of this map, E of xy going to x comma y. What is the kernel of this?
Identity
Kernel.
matters.
No, this is the identity map, but what is the kernel of that? This map is identity map. That is true.
0.
Yeah, it is 0. All right. So we also saw that kernel, a linear transformation T from V to W is injective if and only if kernel of T is trivial. Or in other words, it is generated by a zero element of V. All right. So this is the equivalent condition. And we also saw if let beta and gamma uh, are basis of V and W, and T is a linear transformation. T is a linear transformation, and E beta gamma. Okay, the denote the corresponding the associated matrix to T, then null space of uh, T, null space of the matrix beta gamma is equal to the kernel of T. All right. And second point was the dimension of kernel is equal to the nullity of T beta. All right. So this is what we recalled last time. This is what we discussed last time. And let me uh, let me discuss an example. Okay, I will discuss the example later. Let me also discuss the definition of range. Range of a linear transformation V to W. Okay, so range of T or image of T. It is the short. This is the shorthand notation of image of T. This is image of T. Is defined to be the set of all vectors in W such that where W is an image of some vector V in vector space V. All right. So in set theory, if you guys are familiar with set theory, there is a concept of range and codomain. Okay, so that range and this range is same. There is no difference. And moreover, we say a transformation is surjective if and only if the range of T, which is also the image of T, is the whole space W. All right. So this is the equivalent condition of subjectivity in terms of range. And let me just copy this hypothesis from here. Let beta and gamma be ordered basis of V and W, and T denote a linear transformation, and T beta gamma denote the associated matrix to T. Then the column space of T beta gamma is same as the image of T. In other words, rank of T is defined to be the dimension of image of T uh, is equal to the rank of beta, the matrix T beta gamma. All right. So this is what we have seen last time. And now, because of this associated matrix, we also saw Rank-nullity theorem for linear transformations. Okay. So I'm not going to recall that. Now let me discuss an example. Any questions?
When we say the kernel of T, so when we define that the kernel of T, and this contains this T be equal to 0, does T means the kernel of T means the solution for the T for which this T be equal to 0, or the solution space of this of this equation T be equal to 0?
It basically means set of all vectors in V such that TV is equal to 0. And if you have the associated matrix, right? If you have the associated matrix, then you get a system of linear equation, because then TV will become like T beta gamma times some matrix, okay, some column matrix. So it will become a system of linear equation solving system of linear equation, right? So then it will be uh, then it will become the null space of P. That's what the equivalence is. So,
Oh,
but abstractly, if you want to write it abstractly, then it is not the system of linear equation directly, but for system of linear equation, you need to have an associated matrix, and that associated matrix comes from by choice of basis. Then you will get a system of linear equation. Otherwise, you won't have a system of linear equation to start with. So it is set of all vectors for which TV is 0. In some sense, you are saying whatever you are saying is correct. But in order to make sense what you are saying, you need to associate a matrix to a linear transformation.
yes,
All right?
yes, yeah,
Mhm.
for sure. So we need to
And
have
that's
this
what makes,
TB beta gamma. Okay. Hmm.
yeah, and that's what makes
Yes.
the null space of T beta gamma equal to the kernel of T. So, yeah. So
Okay.
whatever you said makes sense. It's correct. All right. Um,
I missed the last class, did not look into kernel, so I am kind of lost right now. Can you help me understand what is the kernel? If I don't know, that's
so in last session, I've already discussed what kernel was. So if you just bear with me, I will discuss an example, and if it makes you more comfortable with kernels, then let me know. Otherwise, I will try to give another example.
sure. Sure.
All right. Yeah. Uh, so let me discuss this example. Um, so T is a map from R2 to W. Okay. Uh, where W where W is a subspace of R3 uh, satisfying this equation. All right. Now, what are the bases one can find out if you try to solve this system, this equation? You will find out the basis of W to be -110 and -101. All right. So I will call this set because it's on the right hand side. It's a codomain. So I will call this to be gamma. The basis gamma, ordered which is gamma, and on R2,
We can have 0, -1, 1 as well, right?
0, -1.
1.
Yeah, you can have that if you write y in terms of x plus z.
Yeah, yeah.
Yeah. So there are many choices. I'm taking one of such choices and I'm fixing that in order to express. Um, let beta to be 1, 0, 0, comma 1 on R2, and W is given by this with this standard basis, with the basis given by this. Now my question is again same. Yeah, now let me define. So with this, let T is a linear transformation from R2 to W defined as T of xy goes to -3xy plus -3xy minus 3y x plus y x plus y. All right. Now, question is to find the kernel range, find the kernel dimension of range, um, yeah, and check the rank nullity theorem. Rank nullity theorem. All right. So first, in order to do any of these things, we first try to write down the associated matrix. Okay. So I want to write down beta gamma. All right. So for that, I need to express the images of the basis of domain. Now domain is R2. What are the bases? It is standard basis 10 and 01. So image of 10 is, what is the image of 10?
It's -110 times
Sorry?
it's -3. Okay, that's -3 -3. Sorry, -3 1 and 1.
Yeah. And now I want to express this with respect to the basis of gamma. So A times -110 plus B times -101. Right? Now what are A and B's?
A equal to 1 and B equal to 2.
I think A is 0, right? Sorry.
Doesn't seems to be satisfying this. Considering from the
Yeah.
second factor, A plus A is 1, B is 1.
Yes. Yeah. So there is a problem with the solution. So it is 2z. It is 2z,
Yeah.
and the basis is also 2 here. No. So basis is basically 2 1. Yeah. Yeah. So yeah. Now it is fine. Right. Now it is 1 and 1. 1 and 1. It is fine now. So I had a mistake while writing down the problem. So it is 1 1. So it is 1 times 1 0 plus 1 times -2 1. Right. Similarly, 0 comma 1. 0 comma 1 is going to be -3 1 1 again, and again you will get the same coefficients. Right. I'm not writing it again. Now what will be the matrix? So T beta gamma is going to be 1 1 1 1. Right. Now finding the kernel of T is same as finding the null space of T beta gamma. Right. So in order to find out the null space of T beta gamma, what we need to do? We need to first,
Ax is equal to 0, I think.
yeah, Ax is equal to 0 is the null space out of all vectors x comma y in R2 such that Ax y is 0. But how do I obtain this solution? I need to first perform the row reduced echelon form. So if I perform this R1 minus R2, I will get, sorry, R2 minus R1, I will get 1 1 0 0. Right. And now from this, I know that what the solution set? Solution set is
1
x
1. Right.
x is x plus y is equal to 0. That means x is equal to minus y. Right. So it is x plus y is equal to 0. That means x is equal to minus y. So the solution set is minus y comma y y is in R, right? So it is going to be, it is generated by vector -1, 1, right? Is that fine? So that we have found out the kernel. Similarly, for range, you just need to find out what is the row reduced echelon form? Row reduced echelon form of P beta gamma. It was 1, 1, 0, 0. Now, how many pivots variable are there? What is the column rank of this? So, column rank is 1. So, rank of P beta gamma is 1. This implies that the rank of T is also 1 because by definition, not by definition, by equivalent condition, they are same. So, it is also equal to 1. And now, what about the range? What is the range of uh,
The rank of T, right? So that's one only.
the rank of T is 1. Now, what about the range? Range is, uh, yeah, it is going to be,
Range is supposed to be the dimension, right?
no, range is a subspace. Dimension of a range is rank. That is a number. Yeah. Dimension of range is rank. Range is a
Yeah,
subspace.
yeah. Okay. Yeah, got it.
Right. Right. So now let's check for the rank-nullity theorem. Rank-nullity theorem also holds because uh, rank of T plus dimension of kernel should be equal to the dimension of the uh, domain. So dimension of domain was 2, dimension of kernel was 1, dimension of rank is also 1, so it is satisfied. All right.
Dimension of the domain. What's the domain here?
Domain is R2.
Okay. So how is it? Okay. Oh, God. Okay, that was easy.
Dimension of R2 is 2, right?
Yeah.
All right. Okay, now let me discuss another example. Right. So, question T is a map from R3 to R2, and it is given by x, y, z is equal to x minus y plus z, 2x plus y minus z, minus x minus 2y plus 2z. Okay. And assume that uh, beta and gamma. Now find out the kernel and dimension of range of T. All right. So in this case, we will assume that we have a standard basis given. We will express our matrix with respect to the standard basis. All right. And then we will find out the kernel, the and the dimension of the ring. So first step is to write down the base images of the basis of domain. So what are the basis of R3, standard basis of R3?
1 0 0 0 1 0 and 0 0 1, right?
Right. 1 0 0 0 1 0 0 0 1. And standard basis of R2 is 1 0 and 0 1. Right. Now I would like to express the image of the standard basis. So what is T100? Just look
1,
at the
2
expression.
minus 1.
1, 2, minus 1. Good. Sorry, this is a map from R3 to R3. I have written. Yeah, it doesn't make sense. Yeah. So on both hand we have R3 to R3. Yeah. Okay. Now what about the image of 0, 1, 0 and 0, 0, 1? Quickly you can let me know.
Minus 1, 1, minus 2. And
What about
1
0, 0,
minus
1?
1 and 2.
Right. Now I would like to express 1, 2, minus 1 with respect to the standard basis of R3. Again, what will be the coefficients? It will be 1 times E1, 2 times E2, and 3 times and minus 1 times E3. Right? So it will be just each of the coordinate will be the coefficient.
Yeah, and we
So
can write them as columns, right?
directly write down the we can directly write down the T gamma gamma. Let me say AT. So it is 1, 2, minus 1, minus 1, 1, minus 2, 1, minus 1, 2. Right. Now, I want to find out the kernel of this space. So first, what do I need to do? I will transform this. I will perform row reduce extend. I will find out the row reduce extend form of this matrix. Okay, and then count the pivots, non-pivots, independent or independent variables. Find out the null space. Right. So let's perform the row reduce extend form. Perform the row reductions. So what is the first operation that you
R2
would like to
minus
do?
2 times R1.
Okay,
Also do
you will get
R3 plus
1 minus.
R1 cancel.
Okay, so let me do this first. 0, 1 minus 2. 1 minus minus 2, it will be 1,
3.
1 minus plus 3, so it will be 3.
3.
So minus 1 minus 2 minus 3, minus 1 minus 2, 2. Let me do one more operation, which is R3 minus R1, R3 plus R1, right? So what will I get? 0 minus 3,
Minus 3.
3.
3. Yeah. And we can divide
And
the
then,
second column by 3 and the
yeah,
third column by minus 3.
we can add R1 and
Oh, yeah,
R2
yeah.
and
R1 and R2 and R3.
R, and then divide R2 by 3 as well. So 1 minus 1, 1, 0, 1 minus 1, 0. I think the addition is enough. R3 plus R2, 0, 0. Now, what else we can do? We can now add R1, R2 and R. So it will become 0, 0, 0, 1 minus 1, 0, 0, 0. Right?
So, but if we divided the third column by 3, it'll be minus 1, 0, minus 1,
We are not
and 1.
dividing column. We are only performing row operations. We are not doing column operations. We are only performing row operations.
Oh, no, 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 row. If you divide the third row by 3, it'll be 0, minus 1, and 1.
No, I'm adding R3. I'm adding R2 and R3. So we will get 0, 0. And
So,
then you
the
divide
either
by
ways, the rank will be 1 itself, right?
rank is 2.
2? Yeah, 2. So, anyway,
We
it'll
can
be
divide
2, right?
Yeah, it will be 2. There are two pivot variables. and there is non-pivot. There is one non-pivot, or this is one independent
Independent. Yeah.
and two dependent variables.
Two dependent. Yeah, yeah.
So, yeah. So, null space is what is the null space? Null space is precisely this matrix multiplied with x, y, z. You will get the solution set of this. So it will be a vector
X is 0, Y is
x is
Y
0,
is Z, I think.
y and z are same.
Yeah,
Y,
so
z.
0, 1, 1.
So 0, 1, 1. So it is generated by 0, 1. Right? So it is kernel is of one dimension. So kernel of P is given by this. And now, what is the range? Yeah. What is the
Range
dimension
is
of
3, right?
image? The by Rank-nullity theorem, we have the domain dimension of domain is 3. So by Rank-nullity theorem, we will get, and rank is 2, right? Because there are two dependent variables or two pivot elements. So column rank is 2 or rank of matrix is 2. That means the dimension of the range is 2. Dimension of the range, which is also same as the rank of T, which is also same as the column rank or rank of AT, which is 2, right? So yeah, so this completes this question as well. Right. All right. Um, yeah, now there is one more question that I would like to discuss.
So,
Uh,
the rank-nullity theorem for this one is dimension of the kernel and dimension of the range is equal to the codomain. Dimension of the codomain.
Dimension of domain.
Domain. Okay. Thank you.
There is one more question that I would like to discuss is T is a map from R3 to R3. It is an injective linear transformation such that T of 1, 0, 0 is 0, 1, 1. T of 0, 1, 0 is 1, 0, 1. All right. Now, which of the following can be the possible linear transformation? So, first example is first option is T of x plus y is equal to y x x plus y. All right. So so first let me discuss one by one. So is the first one is possible? Can the first one be the linear transformation? Possible linear transformation, which is an injective linear transformation satisfying these two conditions. So first of all, let's check that if I place 1, 0, 0, do I get 1, 0, 1, 1? So
No,
that is
it's not.
true, right? Why? Can you give me the reason also?
0, 1, 0, right? So this is 0, 1, 0 would mean, okay, so you have y. Yeah, it's fine. That is right.
Yeah. So it satisfies both of the conditions, right? It is satisfying these both of the conditions. Uh, so let me name them 1, 2. Satisfies 1 and 2. Right. Now, what about, is there any other condition also that you need to check in the hypothesis in the question? Is there any other condition also?
For 001, we have to check. Sir.
But that is not given to you, right? 001 is not given. Only these two conditions are given. And there is also one more condition, which I have written also, but you are not able to, but you are not telling me.
Is
Yeah,
it that we
yeah,
have to find out if it's a
scalar
linear
multiplication.
transformation?
One by one, can you?
Injective test.
Yeah, injectivity. Injectivity. So this condition is the another condition. So let me write it as the third condition. Okay. So now, does it satisfy the injectivity? Now, how do I check whether it satisfies injectivity or not? All right. So for that, for injectivity, we know that the kernel should
T
be,
of V is equal to 0 if V is equal to 0. We use that one.
yeah, we can use that one also. But yeah, we can use that condition also, or we can use a new condition. We can use another equivalent definition, which is that kernel, the kernel is 0. Kernel is being trivial if it is injective map. And what do we mean by kernel being trivial? If kernel is trivial, that means if the nullity, if we can say the associated matrix nullity uh, is, if the null space is trivial, that means if the nullity is non-zero, that means the kernel is non-trivial, that means it is not injective, right? Okay, so we can use either of the condition. So now, let me first write down the matrix. So it is 1 0 0 is going to 0 1 1. 1 0 1 is going to 1 0 0. 1 0 1. Now, what about this value? If I apply, let's say if you take xy to be 0, because you can see that the image is only dependent on xy, and you take non-zero y, non-zero z. So let's take z to be 1. Now, what is the value? It is, what is the value of the linear transformation?
It's 0, 0, 0.
Right, but it is a non-zero element. So there is a non-zero element in kernel. This implies that 001 lies in the kernel of T. So it is not injective, because injectivity, uh, because T is injective if uh, if kernel of T is just zero vector. Okay, and but there is a non-zero vector in the kernel, so it is not injective. Clear? Now let's look at another transformation. EXYZ given by x plus y, x plus z, x plus 2z, x plus y plus 3z. Okay. Now, what about this? So again, you can check that it satisfies first two conditions. So it satisfies 1 and 2, but it doesn't satisfy the injectivity condition. And how do I see that? So for that, in this case, I will write down the associated matrix. So I will use standard basis on domain and codomain. So let me write down the associated matrix A T with respect to the standard basis of on domain and codomain. All right. So I already know first two values, which is 100 and 01 010. So 100 So I already know two columns. I need to just find out the third column. So it is first column is 100, second column is 101. Now third column is going to be the image of 001. Now what is 001? It is 1, 2, and 3. All right. And now if I want to find out the nullity or the dimension of the kernel, which is same as the nullity of this matrix. So if it has nullity to be not equal to 0, that means there is a non-trivial element in the kernel. That means it is not injective. Okay. In order to be injective, the nullity should be 0. So what is the nullity of this matrix? Can anyone tell me quickly if you perform the row reduction? So first one can perform R3 minus R1 plus R. Okay. What we will get? We will get
So the rank would be 2 and nullity would be 1.
rank would be 2, nullity will be 1. Right.
Yeah.
So that is what we want, right? So yeah, you can obtain the rank row reduced echelon form, and then you can check that the nullity is not equal to 0. All right. So it is a check. So it is again not injective. So it is not injective. Now I am leaving the third as an exercise for you. X, Y, Z, Y plus Z, X plus 2Z, X plus Y plus 4Z. Yeah. So if you, first of all, if you apply this operation, whichever I've written over here, you will directly get 102,000. So you get one nullity equal to 1. So that is what nullity is non-zero. Okay. So third transformation is this. For this also, check find out that whether it satisfies the possible transformation which is injected. So okay, do the same. First, find out the matrix in this case with respect to the standard basis, and then perform the row reduced extend form. And if the nullity is non-zero, then it is not injective. If the nullity is 0, then it is injective. All right. So use the fact that nullity of A is 0, nullity of the associated matrix, nullity of T beta beta, if it is non-zero, this implies, if this is if and only if a statement, it is equivalent statement that kernel or T is nullity is 0 and T is injected. All right. So use this fact to prove that for this and for this another transformation which is given by x plus y plus x plus y plus z. Okay. Is this clear? So I'm leaving these two, third and fourth, for exercise for you guys to do. And I have explained the method. The method remains same as 2. All right. Okay, so I stop here. If you guys have any doubt, question, um, let me know. We can discuss. If not, then you guys can leave. Thank you for joining. Uh, I hope to see you this Thursday.
Thank you. Thank you.
Yeah.
Thank you.
Thank you, sir.
Thank you.
Thanks for joining once again.